Hello and welcome to KTGSK's Urban Garden System Final Design Presentation, presented by Keandra Chambers, Tiffany Paymer, Juliana Lowry, Sarah Stuckless, and Kathleen Souza-Barros.
Today's presentation will discuss our team's solution to the lack of green space that some Toronto residents face. It will detail the following topics. As the City of Toronto becomes more populated, green space is becoming more limited. A lack of green space in urban areas can have far-reaching socioeconomic and environmental impacts. Over the past few months, our team has been researching these impacts and designing a solution to mitigate them. Our vertical automated modular growing system is intended to increase indoor green space in Toronto apartments and aims to improve mental health and food stability. The indoor garden system also has the added benefit of reducing food transportation-related emissions.
Our solution focused on the design of the physical system, as this best aligns with the skill set of the team. The demographic was narrowed down to Toronto apartment residents. The system focuses on edible plants, and 9 specific plants were chosen due to time constraints. The 9 plants chosen are spinach, strawberries, lettuce, basil, tomatoes, cucumbers, onions, ginger, and potatoes. There was a list of criteria kept in mind for this product, but 3 will be focused on for this presentation. User-friendliness. The system should be as user-friendly as possible to further minimize the amount of time the user spends maintaining the system. Ease of system status monitoring. The system should allow for easy monitoring to complement busier lifestyles. User safety features. For ethical reasons, this design should include additional safety features developed into the system to prevent injury to the user. Criteria, there were many constraints, but the 3 that were heavily focused on were system size. The system or product must not take up more than 9 square feet of the apartment floor space and must not exceed 7.5 feet in height. Ongoing consumer cost. The system or product must not cost the consumer more than $80 a month to operate on an ongoing basis. Required user input frequency. The system or product must be able to operate for 2 consecutive weeks without user intervention.
In terms of the design approach, KTGSK's design process consisted of 7 phases. In the first phase, the team conducted research regarding current technologies and specific crop requirements. In the second phase, alternative design solutions were individually developed with respect to the criteria and constraints. This phase was conducted individually to allow free thinking and encourage creativity in the solution development. For the third phase, the team held a group design meeting where each member presented their ideas. In this meeting, the team identified strong components of each design and developed a system that was a combination of the solutions presented. In phase 4, these design solutions were evaluated utilizing a decision matrix and sensitivity analysis with 14 criteria items. The selected design ranked highest in numerous highly weighted criteria such as moisture level and lighting control, user friendliness, user safety features, ease of system monitoring, crop yield reliability, and versatility. For phase 6, the design was refined through multiple iterations, and in phase 7, the design was finalized. A few design tools that were used throughout the design process included the U of G Omni database for research purposes, SOLIDWORKS to develop the detailed system design, the Arduino language library for programming the Arduino, and Figma to develop the app UI prototype. There were 4 designs from Stage 2, including Design 1, the hydroponic tower, Design 2, the modular soil hydroponic hybrid growing system, Design 3, the combination soil compost growing system, and Design 4, the compact and energy-saving smart growing system. The preliminary design consisted of various components from each design, including the water reservoir nutrient and pH monitoring from Design 1, the soil and hydroponic modules from Design 2, the soil moisture monitoring from Design 3, and the flexible lighting arms from Design 4. In addition, the initial basic app features and user interface design was developed. In the second iteration, the module component dimensions and the number of lights were optimized, and specific information from the app display was determined. For the final major iteration, drip lines and hydroponic trays were added to the design, and the app UI prototype was developed.
The chosen design will feature 3 standard sizes, based on plant requirements and needs. The large module will max out at a height of 87 inches, while the medium-sized module, being the widest, will max out at a width of 30 inches. Each module will max out at a depth of 15 inches. Each module will be equipped with 1 to 2 set of light arms with built-in grow light LEDs. The light arms will be able to move up, over, and across the plant to provide optimal sunlight requirements. The LEDs will be based off of a timer, which is predetermined for each plant. Drip irrigation is utilized throughout both the hydroponic and soil module to provide watering for the plants. Hydroponic models will have a separate internal drainage reservoir that will be able to remove the excess water using the drainage valves as seen in the picture. Soil modules will have built-in UV and sediment filters that the drainage water will feed through and then back into the reservoir to decrease the amount of waste. Water, pH, and nutrient additives can be fed through the tubes at the top and into their separate reservoir tanks. Each of the reservoirs will be equipped with an ultrasonic sensor to monitor the levels and notify users if one needs to be refilled. The water reservoir will also store a pH, dissolved oxygen, and water temperature sensor in order to make sure the quality of the water is sufficient for the plant needs. If the water requires more pH or nutrient additive, the Arduino will send the request to the solenoid valves for each of the specific pH and nutrient reservoirs, as seen in the picture at the right, to release the nutrients into the water reservoir to be fed into the hydroponic plants. The picture on the right also displays how the drainage system works by feeding the water directly from the hydroponic modules to its separate drainage reservoir. The area separating both the reservoirs and the actual plants itself will be where the electronics are laid. The image shown displays the filtration system of the soil module. The drained water will go through the sloped basin into the tubes, through the sediment filter, then the UV filter, until it is finally released back into the water reservoir, where eventually it will be pumped back into the system, meaning there will be no waste of water. As can be seen, the filtration system takes up minimal space in the underground portion of the module, leaving optimal space for both the wiring, enclosures, and nutrients and pH reservoirs. The Arduino Leonardo and other electrical components in the underground section of the module will be protected with an enclosure. The enclosure will prevent water from leaking through and other potential damages to the electronics. Wiring from the sensors and LEDs will be routed to this underground portion of the module and into the Arduino enclosure.
The gardening app is controlled by a Bluetooth-enabled Arduino connected to the sensors. Bluetooth along with the app allows the user to connect the Arduino to a Wi-Fi network, and once connected to the internet, the Arduino can then send and retrieve data to and from a database. The user can also now register a module to their account and tell the Arduino in that module what plant type is in it and what maintenance settings to use. This database will hold the pre-made maintenance settings for the 9 plants discussed earlier, as well as any custom maintenance settings, data from the sensors, and user account information. The app in the mobile device gives a way for the user and the gardening system to communicate with each other. It does this by sending and requesting data to and from the database. It displays system information and warning messages and allows the user to update account information, update module information, and save custom maintenance settings. So here's our prototype for the app's user interface. Starting from the left, the first image is the UI showing the user all the systems under their account. Tapping one of these system boxes brings the user to the next UI, which shows the user all the modules within the system and any system warning messages. Tapping on one of the module boxes will bring the user to the next view, which shows specific module information. Here the user can see any module-specific warnings and their current maintenance settings. These settings can be edited and custom maintenance settings can be saved. Having the ability to save and load custom settings allows the system to be used for more than just the 9 plants mentioned earlier, and also allows for further customizability of the pre-made settings.
Our team has done many calculations in order to defend our chosen design. To test the functionality of the VAMG system, 4 main calculations were completed. These included module size, required pump head, required light emission, and module power consumption calculations. The results are shown in this table. To confirm that selected plants could fit within certain module sizes, the plant growing area, growing height, and water requirements were researched. The small hydroponic unit minimum dimensions to support spinach, strawberry, lettuce, and basil plants are shown in the table. The minimum required dimensions for the medium hydroponic unit are also shown in the table. This module was proven to be capable of supporting the tomato and cucumber plants it was designed for. The minimum large soil-based unit dimensions are also shown in this table and were used to prove that the module is the correct size to support onion, ginger, and potato plants. Summing the height requirements for the water tank, growing media, and vertical plant growing space showed that modules needed to be a minimum of 1 foot 2 inches, 2 feet 8 inches, or 5 foot 4 inches for the small, medium, and large modules, respectively. All three required heights are lower than the 7.5-foot height restriction imposed on the modules by minimum Canadian ceiling height building codes. A required pump head of 0.93 meters was calculated for the large growing module. Since the other two module sizes are smaller, a pump with 1 meter of head was shown to perform acceptably for all three module sizes. From plant growing data, it was calculated that module LED lights would need to provide a minimum ppfd value of 471.46 micromoles per meter squared per second. It was confirmed that small enough LEDs could be purchased that would provide this requirement. The overall power consumption of the largest module was found to be 118.04 watts. The current electrical design can safely support this load. Modules are designed with user safety as a top priority. Inorganic growing media was chosen to eliminate the risk of pests and the need for pesticides. All components in contact with crops are food safe, and polymers in the design were chosen from Health Canada's acceptable polymer list and comply with the Government of Canada's food and drug regulations regarding plastics in contact with food. A tipping restraint will be included with each module, and all electrical components are properly isolated from moisture to ensure user safety.
The impact or benefit expected is towards mental health. Being in the presence of plants have shown to improve psychological well-being, as there is shown to be improvement in emotions, behavior, and reduction in anxiety, depression, and other mood disorders. Nurturing plants have shown to lower stress levels and increase energy. Our product aims to improve food security and availability, as it provides easier access to nutritious food. And to fight against climate change, local gardening will aid in the increase of local food production and help reduce the need for outsourcing food to reduce greenhouse gas emissions related to transportation.
The main environmental impact for this design lies in its ability to reduce food miles and thus CO2 emissions. The annual reduction in CO2 can be viewed in the table to the right. As demonstrated, clients can expect to see a reduction in their carbon footprint ranging from 1.1 to 371 kilograms of CO2 annually per module utilized. If 0.1% of Toronto's population were to utilize one module, CO2 emission reductions up to 1,076 tons can be expected, which can aid the city in reducing their carbon footprint and combating climate change on a municipal level.
The initial cost of small, medium, and large units are estimated to be around $690, $1,018, and $1,674 respectively. Medium and large unit prices have more uncertainty in them than the small module price because they were scaled from the small module estimate. We are working to decrease module costs and will be researching other potential product suppliers to bring costs down. Ongoing utility costs associated with operating the product were found to be around $5 a month. The VAMG system is estimated to have a life expectancy of 15 years based off of the approximate lifespan of an Arduino board. With an inflation rate of 1.09% per month as of February 2021, the expected life cycle cost for the VAMG system is $8.77.
There are still a number of uncertainties and risks associated with this product. During the research process, it was difficult to nail down the exact nutrient feeding schedules for each plant. The true yield for plants was also difficult to determine because it is so variable and depends on many different factors. It's hard to quantify the improvement to mental health that this product may cause, although literature does suggest that there is a proven link between plant viewing and mental health improvement. Some risks associated with this project are due to the high initial cost of the modules. Although market research was done to ensure there was a target audience for this product, the market may not be as broad as anticipated. The last main risk I'll bring up is the risk that our company, which manages the database and the app, goes out of business and the modules can no longer be used. There are a number of ways that project risks and uncertainties can be addressed. Prototype testing would allow the team to optimize the plant growing settings and more accurately determine plant yields. The modules could be tested in multiple different environments to increase the number of areas that the system could be used in. Then to ensure there's a market for our product, more time could be taken to find suppliers that will minimize the product cost. Product costs can also be minimized by replacing certain materials for cheaper ones. And lastly, if our company were to go out of business, there's not much we can really do about making sure that our product is still usable, as this requires an app and a connection to a database. However, some possibilities include selling the data in the database to another company that will then maintain a database for the users, or developing a way for the system to be used offline.
Thank you.